Good morning, all the students. Let us start our last lecture of this module so that we can complete the syllabus by today. In the last class, we have seen how to run a job on a cluster by packaging it and deploying it on one of the multiple data nodes, and how to launch a job and also understand about the Mapreduce web UI. Mapreduce web UI is helpful for us to understand the progress in the Mapreduce task. So that Mapreduce page has a Mapreduce user interface has a job tracker, job page, task tracker, task page. The other two we are going to see now. And using this job tracker page and the job page, we'll be able to understand per job what is the job ID, when the job has started, what is the current status of the job, and how many map tasks have run under that job, and how many reduced tasks, and how much of the map and reduced tasks have been completed in terms of percentage, and if any nodes that have failed, and what are the other program counters with respect to how many bytes are read by the map phase, how many bytes are emitted by the map phase, again how many bytes are input to the reduce phase, and how many bytes are output by the reduce phase. All these details can be are available in a consolidated window such as job tracker and task tracker that are available through the Mapreduce web UI. Right? So this Mapreduce web UI is very user friendly in order to monitor the progress of the job execution. Now in today's lecture, we are going to end with retrieving the results, debugging a job, Hadoop Logs, and how to perform remote debugging. Now once the job is complete, you know that a job contains a mapper task and a reducer task, and sometimes if you want to optimize the data transmission between map and reduce, you will also be able to include a combiner function. Now mapper, combiner, reducer, once it is packed into a job and executed on the Hdfs cluster and the job is complete, there are various ways to retrieve the results. You have to retrieve the results, right? What is the objective of our Mapreduce program we have written in this chapter? We have written this program to find out the maximum air temperature recorded in a year across 100 years. Okay, that is our objective. Now, because the input splits will not be processed by a single data node, but the input splits will be distributed onto various data nodes where the processing will be complete and the results will be obtained. Now, the reducer also will emit the results in the form of part files. Later, we have to do some pre-processing in order to combine all those part files to get a consolidated result from the reduce phase. Are you able to follow what I'm trying to tell? The map reduce phase, in the initial stage, the reduce phase will not give a single output. First, it gives the part files which contains the output of all the reduced tasks. Now, these part files have to be, on these part files, you have to perform some pre-processing in order to combine those part files and get a consolidated or comprehensive result out of the entire Mapreduce task. Right? So once the job is finished, there are various ways to retrieve the results. Now each reducer produces one output file. So there are, here we can see in the Mapreduce web user interface that there are 30 map tasks that have been executed, 30 reduced tasks that have been executed. Now out of the 30 reduced tasks, you'll get 30 part files. Right? So if you have some map jobs like this, and these will give input to the reduced jobs, say there are two reduced jobs in this case, then it will give first reduced jobs output as part file 1 and second reduced jobs output as part file 2. But in this NCDC dataset processing, we had 30 reduced jobs that have been executed as part of the job. Now, out of these 30 part files, we'll get out of these 30 reduced tasks, we'll get 30 map files identified by this kind of naming convention. You can see the naming convention here. Part R means it is a part of the reduce task initially the first file is indicated by 0, second file by 1, third file by 2, and so on up to the 30th reduced task output by 29th file, part file 29. And these all files will be saved in the max_temp directory. Max_temp directory is the directory name under which all these reduced task output which are working on finding the maximum temperature recorded in a year across 100 years, that set of part files emitted as output of reduce phase will be taken in the max will be included under the max temperature directory. Now this job produces a very small amount of output, so it is convenient to copy it from Hdfs to our development machine. So this job produces small amount of output when compared to the size of input splits and when compared to the size of data that has been processed by the map phase. You know that map phase will work on the initial huge amount of data, reduce the data into key value pairs before giving it to the reduce phase, and reduce phase further reduces it to give a consolidated output. Now in this case, we know that this job produces a very small amount of output. In this case, we have only 30 part files, right? So it is convenient to copy it from HDFS cluster to our development machine and then produce that consolidated output to the client who is interested in the output of this Mapreduce job. Now the get merge option, there is an option called as get merge option to the Hadoop file system command the get merge option to the Hadoop file system command is useful here as it gets all the files in the directory specified in the source pattern and merges them into a single file on the local file system. So the Hadoop file system command has an additional option called as get merge. This get merge this hyphen get merge option will get all the files in the directory. What is the directory under which the part files are available? Max_temp directory. Now under this max_temp directory, all the 30 part files which have the 30 reduced task output will be extracted, will be taken from the will be taken by using the get merge option and merge them into a single file on the local file system, right? So you will have a file on your local file system ready. Say this is your file on your local file system ready. Now this will receive all the part files which are outputs of 30 reduced tasks, and all those part files will be merged using the get merge option, and all that output will be, that consolidated output will be available on your local machine. Right? This is how we need to get the result, retrieve the result, because the client can't understand the part files separately. But once some pre-processing is done on the part files and all the files are merged, then you can get it into a local file, and that local file can be served to the client who wants the actual consolidated result out of this Mapreduce job. Now we can see how to use this command. We can use a Hadoop command, Hadoop file system command, by using the hyphen get merge option, and from where you are merging the files, the part files are available in this max_temp directory. That is what I have given here, right? The part files which are outputs of the reduce phase are available in this max_temp directory. And that from that max_temp directory, you're fetching all the part files, and through some pre-processing technique, you are consolidating all those results into a local file on the local machine. What is the name of the local file here? Max_temp local. This local file will have the consolidated result of the entire Mapreduce job. Now, if you want to sort the results, because you do not know, you have 100 years data And that 100 years data once merged, remember it is not being sorted, it is just being merged by get merge operation. Now in this max temperature local file, you will have all the years in unsorted format, say 1990, like this. You'll along with their A temperatures that are recorded, maximum A temperatures that are recorded in that year. Now, in order to get them in a specific order to have some meaningful output, you can use the sort method. So you can use percentage sort, give the file that has to be sorted. This max temp local file is now available on your local system. So pass that file to the sort tool. Now it will sort all the data in the max temperature local file and get only the last 10 files out of it. For that, you're using the tail command. Okay, now in this file, you are getting the last 10 years data and maximum temperature recorded in that particular year. Do not worry that the temperatures are too large. Actually, this NCDC dataset provides the output in this format, of which 1/10 of the value we have to consider. So 1/10 of this value is 55 degrees centigrade, and in this value will be 56.8. This value will be 56.7, like this. Okay, so these are all the A temperatures recorded in each year, and last 10 years data we are interested to see whether the data is being properly displayed or not. In order to see that, we display the last 10 records by using the tail command. Now, we sorted the output as the reduce output partitions are unordered. As I said, the reduce output may be unordered. The first reduce may give the 2000 years data, and the last reduce may give 1950s data. The data may not be ordered. In such case, we have to sort the outputs and then give the result to the client. Now, doing a bit of post-processing of data from Mapreduce is very common. It has to be done. Otherwise, the final result may not be much meaningful to the client. So doing a bit of post-processing of data from Mapreduce is very common, as is feeding it into analysis tools such as R, a spreadsheet, or even a relational database. Okay, if you want to do that processing, you can just feed all the data into an R tool or a spreadsheet, which will help us to sort the data in the final consolidated file. Now, another way of retrieving the output, if it is small, is to use the cat command. Cat command will help you to list out what are all existing in a directory. So using this cat option, we can print the output files to the console. Console means to your screen or monitor. Now, how to perform that action? You can use percentage Hadoop file system command -cat and get the max temperature directories, all contents. All content means all the part files of the max temp directory will be displayed. Now on closer inspection, we see that some of the results don't look reasonable. For instance, the maximum temperature for 1951, actually it is not shown here in this case, but say if the maximum temperature recorded in 1951 is 590 degrees Celsius. Here we got all the temperatures in terms of 56.8, 56.7, 55.8. So we have the temperatures here in tens format, right? But if you have it in hundreds, that much maximum temperature is not at all applicable. Nowhere it will be found on earth, right? After 100 degrees it is boiling temperature actually, but if at all due to some erroneous capturing of the data, say the temperature recorded is given as 590 degrees Celsius. Now how do we find out what is causing this erroneous result, and is it corrupt input data or a bug in the program itself that is resulting in such kind of output? That we have to find out. For that, we need to perform debugging of the job. How to debug the job? We can use a debug statement to log to standard error in conjunction with a message to update the task status message to prompt us to look in the error log. The web UI makes this easy. I'll show you where exactly this log file will be found. Now we can use a debug statement so that the log file will get all the standard errors that are encountered while executing the job, in conjunction, in addition, with a message to update the task status message. So what is the status message of the task? Whether the task has been successfully completed or whether the task has been interrupted because of some erroneous data that has been encountered. All this have to be logged or recorded in a temporary file called as log. Now that log will help us to know what is the error that have occurred with the task and how to recover that, or how to distribute, how to transfer the task from that node to another node. For that, in order to perform this task, the web user interface actually makes this easy for us. Okay. Now we can also create a custom counter to count the total number of records with unreasonable temperatures in the whole data set. So there is another alternative. If you don't want to use this web user interface to log the errors and then see what error has occurred, that is one way. The other alternative way is to write a small snippet in your mapper class so that whenever some erroneous temperature is encountered, it should be able to increment a counter. So by the end of the Mapreduce task, that counter will indicate that these many records are, or these many temperatures are erroneously captured, in order to know what is wrong and where it has gone wrong with the temperatures, with that extreme temperatures. In this case, the extreme temperature is 590 degrees, for example, what we have taken. So what is the reason for that extreme temperature? Whether it is bug in the program or whether the data itself is erroneously captured, that details will be clearly understood by writing a small snippet of code in your mapper task. Now this gives us valuable information about how to deal with the condition. If there are too many erroneous data captured, then we can understand that that entire data set might have been corrupted. Or if you get one or two erroneous air temperatures that are recorded, then we may think that only that part of the data is erroneously captured. So we can come to some conclusions based on the information provided, this part of the code that we add to mapper class. Now we add our debugging to the mapper as opposed to the reducer, as we want to find out what source data causing the anomalous output. So how to add the debugging code? The debugging code, remember, should be added only on the mapper side, not on the reducer side, because reducer adds only on the output of the mapper. So by that time, if the mapper have forwarded some erroneous data, reduce also works on the erroneous data and give erroneous results. So in order to avoid that, you should always add your debugging code on the mapper side. Not always, it is suggested to add the debugging code on the mapper side so that the mapper task itself will filter out any erroneous data and give only valid data to the reduce phase, which can work on the valid data and give its final reliable results. Okay. Now how to write this debugging code? See this, in this max temperature mapper class itself, we have written our max temperature mapper, which includes the map function that performs the actual map task on the data set that has been transferred to it for processing, right? Now in that mapper class itself, we can also add some code which will help us to debug what is the source of an erroneous air temperature capturing. Okay, so for that we are again touching this mapper class once again. Now, in this max temperature mapper, you know that it extends the mapper superclass in order to get the map function so that we can override the map function here. In the subclass that extended this mapper superclass, right? So we are extending the mapper superclass and it has a key value pair as input. It takes key value pair as input. So what would be the key value pair for mapper class? It is the file offset and the input split. So the input split looks like this, right? Which has year and the air temperature among many numeric values, right? That is raw data that is captured. which has many other parameters. From that, we are interested just to extract the A temperature and the year in which that A temperature is recorded, right? For that, we take the file offset as the key and the raw input split as the value. So that key is taken as long writable because the file offsets may be larger values as you go on towards ending of the file, and the text value represents this input split, right? Do you remember that? And it also emits output as again a key value pair. So what should be the output here? The year in which the temperature is recorded and the list of A temperatures that are recorded in that particular year. Okay, so that will be taken as the key value pair as output from this mapper class. Now we are adding a small block of code here. What we are doing, we are creating an enumerated data type called as temperature, and we are assigning just one value to it, that is over 100. Now this over 100 variable in this enum data type, enumerated data type is a user defined data type, you know that, right? Now this enumerated data type temperature has have a single value here, that is over underscore 100. We are giving it any name you can give to resemble the purpose for which it is being used as a counter. We are giving over 100. Now over 100 initial value will be 0. You know that in an enum data type, if you have 2-3 values, the values assigned to 2-3 variables, you have the values assigned to those variables starting from 0. Say enum color, if you have, there is a data, I have declared a data type, enumerated data type color, which has blue, green and yellow, right? Now when I create an enumerated data type like this, blue will be assigned 0, green will be assigned 1 and yellow will be assigned 2 by the inherent nature of an enumerated data type. Now we have here only one variable, right? So that will be assigned 0 initially, means you are initializing the counter with 0. Now hereafter, whenever an air temperature that is exceeding 100 degrees centigrade will be counted as one will be taken as one count, means you're trying to count all the air temperatures that are greater than 100 degrees centigrade so that you can consider them as erroneous data that is captured and remove them from the output because they don't have any significant role to play in the final output, right? Because it is erroneous data. Now, after declaring this enum data type, now let us go to another line here. Here we have a private variable NCDC record parser. There is a private variable called written for this NCDC dataset, NCDC record parser. For that class, you are creating an object as the new instance of NCDC record parser. Directly you are taking the records from the NCDC dataset and trying to parse those values. Now you are overriding the actual map function that is already defined in the mapper, already declared in the mapper class. That is why you are giving the annotation override. Now public void, the map function, again receives a key value pair as input and the output will be packed into a context object which can be directly transferred to the reduce phase. I already explained you many times the role of a context object. Context object can serve as a packaging variable where you pack the output of the map phase and transfer it as input to the reduce phase. So this context object travels between different contexts, between the map context and the reduce context. So in order to pack your output into a context object and transfer it to the reduce phase, you use this context method, context object. Now you also have a key and a value pair given as input to the map phase. And let us handle the exceptions by throwing them. Let us make the system handle the exceptions by throwing them as IO exception and interrupted exception. Now, see this line. You are using the parser object. This is the parser object. Parser dot, you're calling the parse method in order to parse the value that is passed. So what is the value that is passed here? This value, the input split that is passed as value that is being parsed so that it can parse out the year and the maximum temperature recorded in that year. Now, if the parser is a valid temperature, you're checking with this valid temperature. Remember, if you write the entire program for Mapper class, you need not use this parser object. But in this case, we are trying to reduce the code, minimize the code. So we are directly using NCDC record parser, which have the ability to parse the air temperature and the year in which the air temperature is recorded. Right? So we are using the parser object, and parser object has a default method is valid temperature, which will check the validity of the air temperature that is recorded. Right? So this is a straightforward usage of the parser object. If parser dot is valid temperature means if a valid temperature is encountered, then from the parser get the air temperature and store it in air temperature. Okay, if the air temperature is a valid numeric value, still we haven't validated whether it is a valid temperature which is not greater than 100 degrees. Still we haven't validated that. We just validated whether it is a valid numeric value, that's all. So when that validity is passed, means the parser encountered a valid numeric value, then from that parser get the air temperature and store it in a variable air temperature. Now our actual debugging process starts. If the air temperature recorded is greater than 1000, as I said, 1000 means 1/10 of this value have to be taken. 1/10 of 1000 is 100 degrees centigrade, right? So 1/10 of this value we are considering. So if air temperature is greater than 1000, then what should we do? How to debug our job? Means what appropriate messages we have to provide to the user. If air temperature is greater than 1000, then print an error message, system.error.println. What should be the message that have to be printed? Temperature over 100 degrees for the input that has been received as key value paired to the map face. Okay, that we need to put it into meaningful sentence. That error have to be put into meaningful sentence so that the client can understand what error has arisen. So temperature over 100 degrees for input value. That value has to be printed. Say if it is around 5670, means you will get a temperature of 567 degrees Celsius. It is greater than 100. So that value will be printed indicating temperature is over 100 degrees for the input. Now after that we need to set the status for the context object. How to set the status? Context.set status. This status will be displayed on your web user interface. Mapreduce's web user interface. So context.set status will help us to pass this message to the user interface. What is the message here? Detected possibly corrupt record. See the logs for further details. Okay, so that status will be passed to the web user interface where the other details about the job are being printed, and context.getCounter also get the counter by incrementing it. So what is the counter we have here? Temperature, the enumerated data type's name, temperature, dot, the variable over 100, you're incrementing it by 1. Dot increment will enable you to increment it by 1 each time the air temperature recorded is greater than 100 degrees centigrade. Okay, so when it is greater than 100 degrees centigrade, then get the counter and pass that to the context object so that these details will be taken to the web user interface and indicate that these many air temperatures are having invalid values because they are greater than 100 degrees centigrade. That details will be passed to the context object through the get counter method. Okay, now after this debugging part is complete, you can write the details, means the key value pairs as output. to the context object to get it passed to the reduce phase. How to write that? Creating a new instance of the text type. You are getting the year from the parser directly. You are getting the year, parser.getYear, and in int writable you have already fetched the A temperature, right? So convert it into int writable. Int writable is integer data type in Hadoop. Text is string data type in Hadoop. Okay, so you are taking the year value in the form of a string and the A temperatures that are recorded in the form of integers and writing them to the context object, and this context object carries this output to the reduce phase. Okay, this is how we write a debugging code. Now, how to understand about the tasks page? The job page has a number of links for viewing the tasks in a job in more detail. For example, by clicking on the map link, you are brought to a page that lists information for all the map tasks on one page. So under a map link, you will have what are all the map tasks. You might have seen in yesterday's class that you have some 101 map jobs executed. Now, if you want to go into details about all these map jobs, then you can click on the map link and further dwell in depth into the details of that each task, each map task. Now, you can also see just the completed tasks. If you want to see the completed task, what is the status of the completed, what are the program counters related to the completed task, on how many data node, data local map tasks are there, how many rack local map tasks are there, that kind of information can be seen from this task page. That can be understood from this task page. So this is a screenshot of the task page. Now, when you click on a completed task, you can go further into details of this task that is executed. Before going into details, let us first understand how this interface, what kind of details this interface provides to us. This is the task ID, map task ID, and the status, how much it is completed, whether 100% or it is aborted in the middle due to some interruption or system failure or a node failure. So that details can be seen here. Here, under the complete window, how much percentage of the map task has been completed is given along with the status here. So if you have some data to be read from the input splits, from which file it has to be read. You know that computation is being passed to the data nodes where the data is residing, not the data passed to and fro within the network, right? So you are trying to pass the computation to the data nodes so that details can be seen here. Okay, to which node you are passing the data, what is the status of the node, whether it is available to perform the map task or it is busy, so that the job tracker have to assign the task to another data node. That details will be displayed here under the status. Now, for example, you can see here the second task, detected possibly corrupt records, see the logs. When the second task is being assigned to the data node, it is not able to access the part of data on which it has to perform the processing. Okay, that is why it detected, it gave the status as detected possibly corrupt record. The data has been corrupted. See the logs for more details, so that the job tracker will understand that this has encountered a data, this has encountered a file part which is corrupted. So it has to assign this computation to another data node where that part of the file is ready for processing. Okay, that can be understood from this status column. Now you can also see the start time and the finishing time of this task, and if any error has arisen, that can be displayed here along with the program counters. This program counters will give us all the details about how many bytes are read as input, how many bytes are read as output, how many of them are data local tasks, how many of them are rack local tasks. That kind of details will be given under the program counters. Now, for all successful tasks, it displays about 10 parameters as program counters to display the details. But you can see here, we have 11 program counters because it also has one more extra details about the error that has occurred in another counter. That is why here instead of 10 in case of successful tasks, it gives us 11 in case of failed tasks, so that the 11th file will have the details about what caused the failure, which node encountered the failure, and how it can be restored. That kind of details will be available in the 11th file. Now, when you click on this task, means this link, when you click on this link, you will further go to task details page. So further details about the task can be known from this page. From the tasks page, you can click on any task to get more information about it. So when you click on this, the task details will be displayed here. Job. This is the job details that are under which the tasks are being executed. You can see here, this is your main job under which all these tasks are being executed. Now, when you click on this task, it will create open a task page where you will have the task ID here, and you will have all the task items that have been listed out. If there is a single task attempt, for that task attempt, the details will be displayed. But if there are multiple task attempts, say that one data node is not free, then it has to assign the task to another data node. That kind of task attempts will be listed under this table. But because this task is successful in the initial stage itself, it has only one task attempt. Now this task attempt and onto which machine this task has been assigned and what is the status of this task. This is succeeded. This task has been completed. 100% completion of the task has been done. So it gives 100%, and the start time of the task, ending time of the task, and if any errors have been encountered, that will be displayed here. And the task logs. So if you want to know if there are any errors that have been encountered, what are the details about the errors, that will be displayed, that will be recorded under this task logs, and the program counters, and finally any actions, extra actions that have been performed, that will be displayed. Now you can also see here the input split locations. So for this task, where are the data, from where the data has been fetched, from which input splits the data has been fetched, that links, that details will be given here, that file paths will be given here. And finally, you will have go back to the job link and go back to the job tracker link. So once you are done with this task details page, you have understood what all are the task details. Now, if you want to go to job page, you can click on this link. And if you want to go to job tracker page, then you can click on this link. Okay, this is how you can understand about a task details page. Now let us see what are the types of Hadoop logs that are available. Hadoop logs will have the details about what has happened during the program execution, during the Mapreduce job execution, what would be the errors that might have been encountered by the map task or the reduce task, and what is the status of that. So how many map jobs have been interrupted due to errors, or how many reduced jobs have been interrupted. All these will be reported in the form of log files. Now, Hadoop creates different kinds of log files, and those log files are targeted to be used by different kind of audience. Okay, so now let us see what are the types of log files and who are the primary audience that are interested in that log files. So you can see here system daemon logs. The first kind of log file is system daemon logs, and administrators, the data center administrators or the system administrators may be interested in this system daemon logs. Now, what kind of details this system daemon logs contain? Each Hadoop daemon produces a log file. You know what are the Hadoop daemons, right? Name node, secondary name node, data node, job tracker, and the task tracker are the Hadoop daemons, 5 Hadoop daemons. Now, each of these Hadoop daemons produces a log file using log4j tool, and another file that combines start, standard out, and error. Okay, so these files will also have some details from standard output and standard error, and this is written in the directory defined by the Hadoop log dir environment variable. So you will be able to find this system daemon logs under Hadoop log directory once this environment variable have been set. Otherwise, these log files will not be available. So if you are interested in the system daemon logs, then you have to set the environment variable Hadoop log directory. Right now, when you go to Hdfs audit logs, this is another type of log file, again in which administrators are interested in, and this is a log of all Hdfs requests turned off by default. Generally it will be turned off. This log file will be turned off by default because it is not a very useful task to log all the HDFS requests, right? Because the HDFS request will be performed, Mapreduce task will be executed, and the final results will be obtained. But HDFS request logs may not be much interested in. So by default, it will be turned off, but it can be turned on by setting that appropriate environment variable. And this is written to the name nodes log, although this is configurable. Means you can write it to a data node also. This log file can be written to a data node also, but by default, it is written to a name node's log itself. You know that name node has all the metadata, right? Excuse me. So you have on HDFS cluster, you have a single name node and multiple data nodes. Now all the data nodes metadata will be stored on the name node. Now in addition to that, you can also make this HDFS audit logs be written to this name node. Though you can sometimes make it to be written to data nodes also, because it is configurable. It is not a static assignment of the log to name node. You can also write it to a data node. And also there is another type of log file called as Mapreduce job history logs. This Mapreduce job history logs users will be interested in. So this kind of log file has the job history of the Mapreduce job. Right? So the users will be interested to see a log of the events that occur in the course of running a job, such as task completion. How many tasks have been completed? What is the progress in the Mapreduce job? In order to see that, these log files may be useful for the users. Now, it is saved centrally on the job tracker and in the jobs output directory in a logs history subdirectory. So you will have a jobs main directory, right? The jobs main directory will have, say, some job identifier as job underscore 111. Under that job, you will have a subdirectory logs. Under that logs, you will have history, which will have the history of this Mapreduce job, right? And there is still another log file which is called as Mapreduce task logs. So if you want to see the log details with respect to tasks executed under a job, then you can go to this log files. And users are maybe interested in this kind of log files. And this contains each task tracker child process produces a log file using log4j called as system logs, a file for data sent to standard output, and a file for standard error. So if any output has been sent to the monitor or if any error has occurred, all the details will be recorded in this Mapreduce task logs. And this is written in the user logs subdirectory of the directory defined by the Hadoop log directory environment. So when you go for this Hadoop log directory environment, along with the system daemon logs, you will also have user logs, which will give us the details about the tasks and the errors that have occurred while performing those tasks. That will be available as the Mapreduce task logs. Now, how to perform a remote debugging. Say, if you want to debug a code on your local system, it is easy for you to do that. But once you deploy your job onto HDFS cluster, as the data is distributed, as the computation is distributed across multiple data nodes, it is very hard to perform the debugging. And if your job has been deployed to a different data center, then it is still more harder to perform the debugging. In that case, you may have to perform remote debugging tasks, because you doesn't have complete control as you do debugging on your local system. You have to do it remotely. So how that can be done? When a task fails, there is not enough information logged to diagnose the error. You may want to resort to running a debugger for that task. Say, when a task has been failed, in such cases, still you're not able to diagnose what is the source that led to this failure of the task. That information is still not available in the log files. Then another extra alternative for you to understand about the failure of the task better is to resort to running a debugger for that task. You have to run a debugger to get extra details to know what is the source of that failure of the task. This is hard to arrange when running the job on a cluster. If you're doing it on a single system, you can run a debugging code and see what raised this kind of error. But when you're doing it on a cluster, it is very difficult for us, as you don't know which node is going to process which part of the input. Right? You don't have any control on it. Based on the job tracker's decision, each map task will be assigned to different data nodes, right? Different map tasks will be assigned to different data nodes. So you don't know which node is going to process which part of the input. So you can't set up your debugger ahead of the failure. That is why before the failure occurred, you can't initiate any debugging process. Only after the failure occurred, seeing the log files, if still the information is not sufficient for you, then you have to run a debugger in a remote mode to find out what is the error that failed this task. Now, often the failing task fails consistently on a particular input, right? So if a task has failed, now, even though you assign different tasks on the same input split, it keeps failing. The failure will be recurrent unless it is rectified. So often the failing task fails consistently on a particular input. Now you can try to reproduce the problem locally. See whether you can reproduce the problem locally, a duplicate reproduction of the problem, and see how you can solve it. Then you can debug it remotely. That will be a strategy to debug the failure that has occurred on the cluster. So you can try to reproduce the problem locally by downloading the file. First, download the file that the task is failing on, download the input split that the task is failing on, and running the job locally, run it once locally on your local machine, possibly using a debugger such as Java's Visual VM. Okay, you can use the debugger, Java's native debugger, Java's Visual VM, and see whether any error can be debugged by running that input split on your local machine. Now, a common cause of failure is a Java out-of-memory error in the task JVM. Sometimes the data node running the task may be out of memory, right? So that may be one common cause for the failure of tasks. So a common cause of failure is a Java out-of-memory error in the tasks JVM, in the task Java virtual machine, means on the node on which this task is running. So for that, you can set mapreduce.child.java.opts to include this entire command. This command will help us to dump what are all the contents in the heap memory. That contents, let us dump it to a file. Later you can see how we can work with that, but initially this task failure can be avoided by freeing the heap memory. Okay, for that what you have to do, you have to set this option mapreduce.child.java.opts options to -XX -heap dump on out of memory error. So if this error has been encountered, then -XX heap dump path to dumps. So whatever is the content which is causing this out of memory exception, that entire content has to be taken as a zipped file and dumped under this directory, path to dumps directory, so that the data will be safe under a subdirectory, but our memory will be freed in order to execute the task without any failure due to out of memory exception. Okay, that is the idea here. Now, this setting produces a heap dump that can be examined afterwards with tools such as JHAT or the Eclipse Memory Analyzer. So, using JHAT or Eclipse Memory Analyzer, later this dump can be examined to see why the out of memory exception arised, whether the resource utilization is not optimized or the resources are excessively being utilized. That kind of information can be understood, that kind of details can be drawn by analyzing the dumped files using Eclipse Memory Analyzer or by using JHAT. Okay, that is later task, but initially we are able to avoid the task failure due to this out of memory exception by freeing the heap memory. Okay, now note that JVM option should be added to the existing memory settings specified by Mapreduce child.java.options. So if you want to add any JVM options, that can be added by this setting, by setting this option Mapreduce.child.java.options. Now, if you want to perform task profiling means for each task, what are the set of resources that are being utilized, how much memory is being utilized, how much processing speed is being utilized. So that resource utilization can be understood by performing the task profiling. For each task, what is the amount of resource that is being utilized? That can be understood by using task profiling. Java profilers give a lot of insight into Java virtual machine, and Hadoop provides a mechanism to profile a subset of the tasks in a job. So you have some subset of tasks that are running under a job, right? Now each of these tasks, how much of the resources they are utilizing, that can be understood by using task profiling. Now also you can use isolation runner. Older versions of Hadoop provided a special task runner called as isolation runner that could rerun failed tasks in situ on the cluster itself. Need not bring the failed task onto your local machine, debug it, see what is the error, and then deploy it back. Need not be done. In older versions of Hadoop, we have a special task runner called as isolation runner, where the job can be run in isolation on the cluster itself. Need not bring it to the local machine. So in some cases, it is useful to keep the intermediate files for a failed task attempt for later inspection, particularly if supplementary dump or profile files, sorry, I haven't formatted this properly, but you can easily read it. Particularly if supplementary dump or profile files are created in the task working directory. So in some cases, better not dispose the intermediate files. Say you have intermediate files when the Mapreduce tasks are executing, right? So that intermediate file, sometimes keep them up to some extent of time so that these failed attempts can be better understood from those intermediate files by inspecting them in the later stages, particularly if supplementary dump or profile files are created in the task working directory. Then it is easy for you to debug what is the failure source. Now you can set keep failed task files to true to keep a failed task files. Got it? So if any intermediate files are associated with a failed task, then in order to keep them and inspect them in the later stages, you can enable this option, keep failed task files option to true. so that that intermediate files will be kept as it is until you dispose them, to understand what is the error that caused this task to fail. Now you can keep the intermediate files for successful tasks also if you want, which may be handy if you want to examine a task that isn't failing. Now sometimes if you are interested in why a task is failing, you can keep those intermediate files. Sometimes it may be necessary to keep the successful task to know why the task is not failing. That is also an important step, right? So if you know why the task is not failing, you can also recommend some changes to the failed task in that way, so that they need not fail in the future, right? They should not be failed in the future. For that, in order to understand the successful tasks, why they haven't failed, for that also you can retain the intermediate files for the successful tasks also. Now in this case, set the property keep task files pattern to a regular expression that matches the IDs of the tasks you want to keep. You can't store all the task details, right? So some tasks where you guessed some error may happen, but actually the task executed successfully, then you might be interested in how the task has executed, overcoming some exceptional case. In such cases, you have to give a regular expression by assigning it to keep.task.files.pattern. If you assign a regular expression to it, that regular expression will filter out which files. Say that a regular expression may have all the files under Hadoop task logs. So this regular expression, if you give, all the files under this directory will be filtered out, and all the files not under this directory will not be filtered. Okay, in that way you can get the intermediate file details for the tasks that have successfully run. Now to examine the intermediate files, log into the node that the task failed on and look for the directory for that task item. That is another easy step. In order to go in depth into the intermediate files, in order to examine the intermediate files, you have to log into the node that the task failed. Means that node has the data copy on which the task is running. Now the task has failed on the data node, so you can log into the intermediate file and look for the directory for the task attempts that has been made that led to the failure. So you can easily understand what has led to the failure. Now it will be under one of the local Mapreduce directories as set by the Mapreduce local directory property. So once you set this mapreduce.local.directory property, that intermediate files will be available under the local Mapreduce directories itself, so that you can go into it and examine what is the source of the failure. Now, if this property is a comma separated list of directories, then you may need to look into all the directories before you find the directory for that particular task item. Sometimes you may have under a directory again a list of directories for multiple task attempts. So you have to find out what is the appropriate task you are interested in order to examine the intermediate files. Now the task attempt directory is in the following location. So if you want to find out where exactly the task attempt directory is available, you can just see the directory structure like this. This would be the directory structure where you can find the task attempts directory. Mapreduce.local.directory. Under that you may have a task tracker subdirectory. Under that you may have a job cache subdirectory. Under that you will have a job ID under which the task attempt has been made and it has failed. Okay, so it will have the task attempt ID. Whether it has failed or successful, you can go into it and examine what are the reasons for its successful execution or what are the reasons for its failure, right? Now let us quickly paraphrase what we have covered in this fifth module. We have seen what is a Mapreduce framework and the weather dataset data format, how the NCDC dataset looks like, and how to analyze the data using Unix tools, and how to analyze data with Hadoop's Mapreduce, and how to write the Java Mapreduce programs using the mapper class and a reducer class, which further has the map function and the reduce function, which will have the code to actually perform the map task and reduce task. And after that, we have done this on a local machine. Now, how to scale it out onto a larger cluster we have seen, and how to optimize the data flow between mapper and reducer using a combiner function, and running a distributed MapReduce job also we have seen, and how to use Hadoop pipes to write a C++ code to run the MapReduce task, and developing a MapReduce application, how to configure the API by adding the resources in the form of XML files, .xml files, and how to combine multiple resources, how to combine multiple .xml files in order to configure how to configure the data nodes on which the MapReduce job would run. Okay, that we have seen in these two concepts, the configuration API and the combining resources concept, and how to perform variable expansion and setting up the development environment, how to set up the development environment in order to run the MapReduce job on a Hdfs cluster, and how to use generic options parser so that we can set the configuration parameters from the command line rather than by passing them as by giving the properties through configuration API. If you want to reset them by using command line argument, how can you do that by using generic options parser that we have seen, and how to write unit tests with MapReduce unit package so that we can test our code, MapReduce code at a local machine level itself and run it locally by using some test data, and how to test the drivers by using a driver code, by writing a driver code, how to test the drivers, and how to run it at a larger scale on a cluster and launch this job onto Hdfs cluster, and also understand about the MapReduce web user interface, how a job tracker page, how a task tracker page looks like, and finally how to retrieve the MapReduce jobs result into your local machine by performing some pre-processing on the part files that can be written under the MapReduce directory. And finally, how to debug a job and debug it remotely also. Whenever it is deployed onto Hdfs cluster, then how to debug it at a remote level rather than debugging your job on your local machine. Okay, all these topics are covered in your 5th module. I hope all of you have received the notes for module 3, 4, and 5. So it will be easy for you to just go through the lecture notes and recollect what have been learned during the online sessions or during your classroom sessions. Any doubts so far, students? Okay, just go through the videos and the notes. If you have any doubts, you can call me also or WhatsApp. I'll try to solve your problems. Okay, I'll stop recording and take attendance.